Welcome to the section Introducing Computer Vision. In this section, we will discuss topics from computer vision. I start with the basics of computer vision, showing how to work with images using the Python Image Library, or PIL, Numpy, and Matplotlib. Then I introduce OpenCV, a popular package for common computer vision tasks. Then I show how to apply filters and transformations to images to present them in new ways. I illustrate finding interesting points in images, such as corners or faces. I demonstrate scale invariant feature transform, or SIFT, as a more robust corner detection algorithm. I illustrate how to create an image search algorithm. Then I conclude the section with showing how to perform optical character recognition, or OCR, using the Tesseract package. Let's not waste any more time. Let's talk about computer vision. In this video, I introduce computer vision. I provide basic concepts, then show how to load and manipulate images in Python using the Python Image Library, or PIL, Numpy, and Matplotlib. In computers, images are usually considered in one of two ways. The most common view in computer vision is the raster version. In raster images, the image is a collection of pixels on a grid, with each pixel being viewed as a combination of red, green, and blue intensities, called channels, that together determine the color of the pixel. The intensities of each of these colors range from 0 to 255, so there are 256 possibilities for a single channel. Together, there are 2 to the power of 24 possible colors a computer can understand. File formats such as JPEG or PNG store raster images. Vector images are less common in computer vision. An image in this case is a collection of mathematical formulas describing lines and color gradients. While resizing a raster image will reveal the pixel structure, resizing a vector image causes the lines to be rendered on a different scale. Vector images are stored in files such as SVG files. We will not discuss vector images in these videos. That said, converting a vector image to a raster image is simple. Let's now move on to the notebook demonstration. First thing I'm going to do is load in all the libraries I'm going to be using, and in particular I'm focusing on PIL, and I'm going to use PIL to look at the image of a house using Matplotlib used in the plt.imshow function. Here's the resulting house. Now let's say I don't want to see this house in color. Let's say I want to look at it in grayscale instead. We can convert the house to grayscale. Now that said, that doesn't mean that what we'll see is a gray image. Instead, what we see is an image that looks like this. This is mostly the responsibility of Matplotlib. It has decided it wants to show images in this format. So let's see in different formats. For example, here's using the hot map to really draw out spots of bright intensity and make the darks look somewhat dark. But what is dark here is just very red. And here's your typical gray image. This is how we usually think of grayscale. So those other mappings are useful for seeing the picture in different ways where you can see details that you might not see before. Now if you wanted to, we could rotate the house. Here is a rotated version of this image. We rotated it 45 degrees. Now here's resizing the house. Now we're going to see a 16 by 16 pixel version of this house. So now this is an individual pixel and it's a large block. This is how the house would look like as a 16 by 16 image. Here's a subimage when we crop the house. So this is the house where we look at the square that starts at the corner with coordinates 200, 200 and has the other corner at coordinates 500, 500. This is the resulting subimage. We can even transpose this so that it's upside down, and we can even paste it in another image. So here is the house image, but now we have pasted in a version of what used to be in this square. Now, Numpy is capable of storing image data. We can create Numpy arrays that store the RGB values of the image. So what we have is an image with the same width and the same height, and this array has a depth of 3. So we can actually think of this as being 3 arrays. So here is the upper 5 by 5 corner from all 3 channels. And this is channel 1, this is channel 2, this is channel 3. And we can see what the red channel looks like for the house. And here's the green channel. And here's finally the blue channel. And doing this 255 minus results in the channel looking how we would actually imagine it looking like. If I were to remove this code, here's what we would actually see. It would be kind of inverted just by how matplotlib is plotting things. Something that's very interesting to look at when you're looking at images is histograms. This tells you what pixel intensities within certain channels appear in an image and how frequently they do. So we can see, for example, the intensity of reds and what intensities we see most often. So there's a spike around here indicating many light colors. The greatest intensity leads to light colors. So there's a lot of like white-ish pixels. Here is the green channel, and here's the blue channel's histogram. SciPy works fine with Numpy arrays, so since we can view an image as being basically a Numpy array, we can use SciPy and all of the tools that come with it. So for example, I have written a couple functions, and this is actually from a previous video course that I did, but I've written some functions that allow for interpolation so that you can resize an image without getting the giant squares that we saw earlier. So I'm going to run these functions, and I'm going to do first the cubic interpolation so that we can see what the resulting array looks like. So if we were to see the resized version of the reds section of the house, without doing this interpolation, this is what we see. We see the blockiness, and we don't necessarily want the blockiness. So we can apply this interpolation to the new image, and here's the result. This is somewhat smoother, so we get what looks slightly better when we resize the image.